Welcome back to the Deep Dive.
Glad to be here.
Today, we actually have a mission specifically for you.
Yeah, a really interesting one.
Right, because whether you are, actively designing enterprise architecture, or maybe prepping for some major deployment meeting, or honestly, if you just want a masterclass in how the invisible plumbing of our modern world actually functions, you are absolutely in the right place.
You really are.
Because we are looking at a stack of documents today that, well, on the surface, they should be the most boring texts on Earth.
Oh, absolutely. Mind-numbingly boring if you don't know what you're looking at.
Exactly. I mean, we're talking about IT pre-installation surveys, deployment checklists.
The real dry stuff.
Right. The forms where you plug in your subnets, you agree on a Linux distribution, maybe check a few boxes, and then you just wait for the deployment script to run.
We usually just treat these as administrative hurdles, just paperwork.
But the thing is, when you apply this exact paperwork to the modern, massive-scale AI infrastructure being built today, well, the routine checklist completely shatters.
It really does. It shatters because the underlying reality, the hardware, has just fundamentally changed.
Yeah.
What we are analyzing today are the actual deployment surveys and operational requirements for a system called SuperCloud Composer, or SCC.
SCC, right.
When you look at the pure math in these forms, the network allocations, and especially the incredibly specific warnings embedded in these drafts, you are looking at the bleeding edge of data center physics.
It's crazy. It is a literal blueprint for survival in a high-density environment.
Blueprint for survival is a great way to put it.
So we have gathered the entire stack of these sources, right? We've got drafts of site surveys, network allocations, operation requirements.
All of it.
And we are going to deconstruct these forms to show you how the pivot from traditional cloud computing to, heavy AI workloads is completely rewriting the rules of infrastructure management.
And that transition, it is highly physical. By unpacking what SuperCloud Composer requires simply to exist and just monitor a network, we are going to see the sheer scale of the beast that it has been built to manage.
Right.
We really need to start by looking at the hardware required to run the SCC platform itself.
Yeah, let's start there.
Which is specifically detailed in Draft 1 and Draft 4 of our sources.
Okay, let's unpack this hardware spec situation because the text establishes this stark contrast almost immediately.
It draws a very hard line.
It does. It draws a line between traditional air-cooled environments where you are, monitoring standard system states, network devices, maybe basic power equipment, and modern AI workload infrastructure.
Which is a whole different ballgame.
Totally different. The language in the document pivots entirely to, quote, high-volume GPU telemetry and higher capacity networking and specialized cooling technologies.
Yeah, the phrasing alone tells you something has shifted.
And the hardware required just for the SCC management worker nodes, it is staggering.
Keep in mind, these are just the watchers of the system.
Right. They aren't doing the AI training.
No, they're just the nodes responsible for ingesting the telemetry, just watching.
So, okay, the minimum specs for a basic proof of concept, they ask for a 16-core CPU, 64 gigabytes of RAM, and half a terabyte of storage.
And that's just the minimum.
Right, running on Ubuntu 22.04 or 24.04, maybe RHEL 9.4 through 9.6, or Rocky Linux 9.
Standard enterprise Linux stuff.
Yeah, but the recommended specs for a large deployment, that is what really caught my attention.
Oh.
Dual Intel Xeon Platinum 8368 32-core processors.
Dual 32-core processors. Let that sink in.
128 gigabytes of RAM.
Yeah.
10 gigabit Ethernet networking. Terabytes of NVMe storage.
For a monitoring tool.
Exactly. We are talking about a platform that only monitors other computers. I have to push back on this kind of provisioning because
That's like overkill.
It sounds like insane overkill. Managing traditional IT is like being a traffic cop at a suburban intersection, You watch the flow, you flag an anomaly if someone runs a red light. But managing AI infrastructure based on these specs, it's like running air traffic control for JFK Airport during a hurricane.
That is a highly accurate analogy, actually.
But why? Why does a management overlay require dual 32-core Platinum processors?
Well, to understand the provisioning, we really have to look at the mechanics of telemetry ingestion at an AI scale.
Okay.
We basically have to leave behind the legacy concept of SNMP polling.
Right, simple network management protocol.
Exactly.
Yeah.
In a traditional environment, a monitoring tool queries a server, maybe once every few minutes.
Yeah. Hey, how are you doing?
Right. It checks CPU utilization, disk space, memory overhead, and if a threshold is crossed, it generates an alert.
Simple.
The data payload is microscopic, and the frequency is super low.
It's a very highly relaxed sort of conversational loop between the watcher and the watched.
Exactly. But these SCC documents, they're describing AI clusters built on system nodes with 8 GPUs per node.
8 massive GPUs.
These are not standard compute environments. You have these interconnected GPUs relying on ultra-high bandwidth fabrics.
Right.
So the data points being generated every single millisecond. We're talking core temperatures, HBM memory temperatures, power draw, voltage step-downs, liquid coolant flow rates.
Oh, wow. Even the liquid cooling metrics.
Yes, and individual fabric link error rates. The sheer volume of that data is astronomical.
So the watcher isn't just polling for a casual status update anymore.
Not at all.
It is trying to map the velocity of every single raindrop in that hurricane in real time.
That's it, exactly. And the reason for that intense density of data collection is the physical fragility of a synchronized AI workload.
Fragility? Really?
Yeah, I mean, if you are running a distributed training job across thousands of GPUs, and one single GPU in one node hits a thermal limit.
It gets too hot.
Right, it immediately throttles its clock speed to prevent physical damage. It protects itself.
Makes sense.
But because the training workload is deeply synchronized, the moment that single GPU throttles down, the entire cluster across thousands of nodes has to stall and wait for it to catch up.
Wait, really? The whole thing?
The whole thing.
So the bottleneck just cascades instantaneously across the entire network fabric.
Instantly. You lose massive amounts of compute time. Therefore, telemetry isn't just a dashboard for administrator to sip coffee and glance at.
Right. It's not a passive display.
No, it is mission-critical data that is used to dynamically manage the cooling and the workload distribution.
So SCC is doing heavy lifting.
SuperCloud Composer is receiving millions of JSON payloads a second.
Millions.
Millions. It has to ingest that data, parse it, write it to a time series database, and then run alerting algorithms against it without a single millisecond of latency.
Okay, so that explains the silicon.
Right. The dual 32-core Platinum processors, they're necessary simply to parallelize that data ingestion.
Just to catch all the data being thrown at it.
Exactly. If the CPU cache bottlenecks, or if the memory bandwidth on those 128 gigabytes of RAM maxes out,
the monitoring platform drops packets.
It drops packets.
And if you drop telemetry packets during, say, a 100 kilowatt power spike,
which happens in these environments,
then your multi-million-dollar AI cluster is flying blind at the exact moment it is most likely to suffer a catastrophic hardware failure.
Exactly. The watcher must be mathematically capable of swallowing the total data output of the cluster.
Which is why the SCC sizing is tied directly to the node count and the telemetry volume.
You've got it.
Okay, that reframes the entire purpose of the platform for me. We are really looking at an industrial control system here.
Yes.
Not just a software dashboard.
Not at all.
And this translates directly into the physical geography of the data center, doesn't it? Which is mapped out extensively in Draft 1, Draft 4, and Draft 5.
It really does. The spatial logistics are where the physics truly start to constrain the deployment.
Because the physical layout of the racks directly dictates the software architecture of SCC.
If we connect this to the bigger picture, the physical real estate is the hardest limit they face.
So looking at the sizing examples in the source material, it forces you to do some complex math.
Yeah, it's not simple addition.
No. Example 1 outlines an AI infrastructure with 512 system nodes at 8 GPUs per node.
A decent-sized cluster.
But they are spreading this across 128 racks.
Yay.
Which means they are only placing 4 nodes in each rack.
Only 4.
Then they add 128 TOR switches, top-of-rack switches, 128 CDUs, which are the cooling distribution units, right?
Correct.
And 256 PDUs, the power units. Plus a few racks for networking and storage, totaling 132 racks.
That's a huge footprint.
And managing this baseline large deployment requires 3 SCC masters and 2 to 3 worker nodes.
And then the documents scale that up to example 3, which represents a massive facility.
The real giant.
Right. 2048 system nodes spread across 512 racks with 512 CDUs and 124 PDUs, totaling 528 racks.
Wow.
And to manage that footprint, SCC demands 3 masters and 8 to 12 worker nodes.
Just to watch it.
Right. And the architecture mandates Kubernetes high availability, or HA.
Which means what, exactly?
It requires a minimum of 3 control plane nodes and shared storage, like CEPH or NFS, just so the management layer never goes down.
Okay, I have to challenge the rack density in these examples, though.
Okay, go for it.
Because there is a specific architectural note in the text stating that customers may choose to spread AI infrastructure across several hundred racks rather than fully populating each rack.
Yes, that is a critical note.
But in a modern data center where floor space is wildly expensive, deliberately leaving rack space empty seems completely counterintuitive.
It does seem crazy to traditional IT folks.
Right. Why only put 4 nodes in a standard 42U rack that could physically hold significantly more hardware? You're paying for the space.
Well, the limitation has absolutely nothing to do with physical volume.
It's not about how big the boxes are.
No, it has everything to do with power density and thermal dissipation.
Heat and electricity.
Exactly. A traditional enterprise server rack might be provisioned for maybe 10 to 15 kilowatts of power total.
Okay, 15 kilowatts max.
But a single modern 8-GPU AI node can draw over 10 kilowatts by itself.
One node.
One node. So if you were to fully populate a 42U rack with these nodes, you would be looking at a power draw exceeding 100 kilowatts for a single footprint on the data center floor.
Over 100 kilowatts in one rack space.
Yes.
I mean, most legacy facilities physically cannot route 100 kilowatts of power to a single tile.
They absolutely cannot.
The busways and the backup generators, they simply aren't sized for that kind of concentrated amperage. The wires would literally melt.
They would. And beyond the power delivery, you have the thermal nightmare.
Right, because all that power turns into heat.
Exactly. Generating 100 kilowatts of heat in a single rack requires incredibly aggressive liquid cooling.
You can't just blow a fan on it anymore.
No, air cooling is completely dead at this scale. You need massive cooling distribution units, the CDUs we mentioned earlier.
Yeah.
And these CDUs have to interface directly with the facility's water loop to extract that heat via cold plates that are physically attached to the GPUs and CPUs.
Oh, wow. Cold plates directly on the silicon.
Yes. So if the customer's facility doesn't have the plumbing or the heavy chiller capacity to handle 100 kilowatts per rack, they are forced to spread the 512 nodes across 128 racks just to keep the thermal density manageable.
So spreading it out solves the thermal issue, but it seems like it creates a massive logistical headache for the monitoring platform.
That is the exact downstream consequence.
Yeah.
By expanding the physical footprint to 128 racks instead of condensing it, you have drastically increased the number of PDUs, CDUs, and top-of-rack switches.
Oh, because every rack needs its own support gear.
Exactly. SuperCloud Composer doesn't just monitor the compute nodes. It has to monitor all of the environmental infrastructure, too.
The pumps, the power blocks.
Right. So you have the exact same amount of compute power, but the management software suddenly has to ingest telemetry from 128 separate cooling distribution units and 256 separate power distribution units.
The sheer volume of endpoints just explodes.
It scales exponentially with the physical spread.
Which perfectly explains why the SCC worker node count scales all the way up to 12 in the larger examples.
Exactly. The physical architecture of the facility dictates the software scale of the Kubernetes cluster.
And reading between the lines, it forces a critical architectural decision for the customer.
That absolutely does.
Because for a massive deployment like example 3, covering over 500 racks, the customer has to decide how to actually structure their management plane.
Right. They have a big choice to make.
They can build one giant SCC Kubernetes cluster to monitor the entire facility, or they can split it into multiple SCC instances separated by like data hall or fault domain.
So basically running 4 separate SCC deployments based on example 1 rather than one monolithic deployment for example 3.
Right. Why would they choose to split it up?
Well, it depends on the network latency between the data halls and also the organization's disaster recovery posture. Because relying on a single control plane for 500 racks of AI compute introduces an unacceptable blast radius.
Blast radius meaning if it goes down, everything goes down.
Exactly. If the core management network fails, you lose visibility into thousands of GPUs simultaneously.
And they are pulling 100 kilowatts, so you don't want to lose visibility.
You'd be totally blind to thermal events. So segmenting the SCC deployments confines any management plane failure to a single fault domain.
It's a safety measure.
It is.
Which honestly introduces the insane complexity of the internal network architecture.
Oh, the networking is where it gets really tense.
Because if you are managing 500 racks of liquid-cooled hardware, connecting all these moving parts without causing a catastrophic routing collision is paramount.
Absolutely paramount.
And this is where Draft 2 and Draft 6 detail the network addressing overview. And I have to say, the tone of the documentation here borders on absolute paranoia regarding network isolation.
Paranoia is the right word. The requirements for these non-routable isolated subnets are incredibly rigid.
It's very rigid. The SCC system relies on massive internal Kubernetes networks.
Yes.
The Docker BIP, the bridge IP on the Harbor VM sits on 172.117.0.116.
Okay.
The core Kubernetes cluster subnet uses 10.42.016.
Right.
And the Kubernetes service subnet uses 10.43.0.016.
Huge subnets.
Massive. And the text contains this severe warning. It says, quote, overlapping CIDRs may result in traffic being inadvertently routed outside the SCC host boundary, potentially impacting routing behavior and platform operations.
That's a very polite way of saying the system will crash.
Exactly. And confirming that these internal IPs do not overlap with any organizational networks is listed in Draft 6 as a hard gate for customer sign-off.
A hard gate?
A hard gate, meaning you don't sign, we don't build.
Right. It is a completely non-negotiable prerequisite. To understand why a CIDR collision is a hard gate, we have to look at the routing mechanics of Kubernetes itself.
Okay, break that down for me, because I understand the need for isolation, sure, but reserving an entire 16 subnet gives the cluster roughly 65,000 internal IP addresses.
Yes, it does.
Why does a single management platform require 65,000 addresses purely for internal cluster communication? That seems like hoarding IPs.
It really comes down to pod churn and the nature of east-west traffic.
East-west meaning internal traffic within the cluster.
Exactly. Kubernetes breaks the SCC application down into tiny microservices running in ephemeral pods.
Ephemeral, so they don't last long.
Right. You have pods dedicated to UI rendering, pods for time series database writing, alerting logic, API gateways. It's all split up.
Yeah.
And in a high availability deployment, you have multiple replicas of all these pods distributed across the worker nodes.
And each of these pods requires its own unique IP address to communicate across the internal overlay network.
Yes, every single one. Furthermore, these pods are not static.
They move around.
Constantly. During a software upgrade or a node failure or just horizontal scaling, Kubernetes destroys pods and spins up new ones instantly.
Oh, wow.
And every single time a new pod is scheduled, the Container Network Interface, the CNI, allocates a brand new IP address from that 16 pool.
Okay, so it burns through them fast.
Very fast. If you restrict the cluster to a smaller subnet, say a 24, which only gives you 254 addresses,
you'd run out.
You will absolutely exhaust the IP pool during a period of high pod churn.
And then no new pods can spin up.
Right. The system needs the massive overhead of a 16 to guarantee IP availability for these ephemeral workloads at all times.
Okay, so the cluster subnet handles the dynamic pod-to-pod communication.
Yes.
While the service subnet, the 10.43.01016, that provides the stable virtual IPs, right? So traffic knows where to route regardless of the pod churn underneath.
Exactly. The service layer abstracts the ephemeral pod IP so things can find each other reliably.
Okay.
But here's the danger. If an enterprise customer ignores that hard gate,
the overlapping IP warning.
Right, and they inadvertently use a 10.42 subnet somewhere else in their corporate network.
Oh, yeah.
Say perhaps for a remote branch office or maybe an internal HR server.
Just a standard corporate server.
Yeah. If they do that, the routing tables within the SCC nodes become instantly corrupted.
Okay, let's walk through the actual mechanics of that failure, because it's like having two houses with the exact same address in the same city.
That's a great way to picture it.
So, if a telemetry ingestion pod tries to forward data to a database pod using an internal IP in the 10.42 range, and the host operating system routing table sees that the 10.42 CIDR is advertised via BGP to the corporate wide area network, what happens?
The internal east-west traffic is inadvertently routed north-south.
Out of the cluster.
Yes. The critical telemetry packet leaves the encapsulated Kubernetes network, it hits the default gateway, and it gets routed out to the corporate network, head straight toward that HR server.
Just flying out the door.
Exactly. And the internal database never receives the data.
So the data is just lost.
The pods cannot communicate, the control plane loses quorum because it can't talk to itself, and the entire monitoring platform collapses.
You essentially breach the digital containment dome.
You fracture the internal routing logic completely. This is exactly why Supermicro requires absolute confirmation that the SCC Appliance Management Network, which is the external-facing interface, is perfectly isolated from the internal Docker and Kubernetes subnets.
The telemetry loops just have to remain completely self-contained to guarantee stability.
If they aren't, the whole thing falls down.
So we have this deeply isolated, hyper-complex Kubernetes environment, right? It's ingesting millions of telemetry data points to manage the literal physics of an AI cluster.
Yeah.
But eventually, this closed loop has to interface with a human operator.
Right. Someone has to fix the hardware when it breaks.
Like when a CDU pump fails or a GPU throttles, a human needs to know.
Exactly.
And this brings us to the operational requirements in Draft 7, which dictate how the platform communicates outward to the human.
This is where we see the fascinating intersection of modern AI telemetry and legacy enterprise protocols.
Here's where it gets really interesting to me. The juxtaposition is just glaring.
It's pretty funny, honestly.
We are talking about dual 32-core processors, liquid cooling loops, AI hardware, and the SCC operation requirements mandate integration with SMTP for alerting.
Good old-fashioned email.
Email. The survey literally asks for relay ports, 25 for internal, 465 for SSL, 587 for TLS.
Standard mail ports from decades ago.
And it requires Active Directory integration via LDAP for role-based access control, or RBAC.
Yep.
You have a platform analyzing thermal dynamics across 2,000 GPUs in real time, and its primary method of alerting a human that something is melting is sending an email.
I know, it sounds almost absurd when you put it like that.
It does. Are humans just the weakest link here?
Well, what's fascinating here is that it highlights the hard reality of enterprise infrastructure.
What do you mean?
No matter how incredibly advanced the internal processing of the AI cluster is, the notification layer eventually has to integrate with the customer's existing compliance and auditing frameworks.
The corporate IT standards.
Exactly. SMTP and LDAP are universally supported. Every single enterprise on Earth uses them. If Supermicro required some custom API integration just to send a basic alert, you drastically increase the friction of deployment.
It would take months just to get the security team to approve the new API.
Precisely. So they use email.
Okay, the reliance on standard protocols makes sense for integration, but the documents also reveal a deep, almost funny anxiety about the human element handling these integrations.
Oh, the password warning.
Yes. There is a security note repeated in bold multiple times throughout these Excel spreadsheets.
Big red letters.
It says, quote, security note. Do not enter passwords in this spreadsheet or email. Passwords should be provided separately using the customer's approved secure communication method.
Which is such a human problem to have to solve in an AI document.
Right. The cryptographic protocols securing the AD handshake are mathematically sound. The Kubernetes namespace isolation is rigorous.
Impervious, practically.
But the absolute weakest link in the entire deployment chain is the tired network engineer filling out the intake form.
Exactly. Because an engineer trying to get a 40-page survey approved by, Friday afternoon deadline is highly incentivized to simply type the bind password straight into the Excel cell rather than coordinating a secure secret transfer.
It's just faster to type it in and hit send.
Supermicro anticipates this human bias toward convenience over security.
They know it's going to happen.
If an Excel spreadsheet containing the LDAP bind credentials and the SMTP authentication passwords sits in an unencrypted email inbox, well, the entire security posture of the SCC appliance is completely compromised before the physical hardware even arrives on the loading dock.
The hackers just search the email server for the spreadsheet and they have the keys to the kingdom.
Exactly. The bold warnings are a desperate attempt to enforce operational discipline during the planning phase.
They are literally trying to patch human behavior with a yellow warning box in Excel.
Oh, that's exactly what it is.
Amazing. Now, there is another crucial detail regarding SMTP and the operational requirements that stood out.
Which part?
The document mandates a temporary setup where, quote, commissioning alerts are routed outside the customer's domain directly to a Supermicro corporate email address.
Yes, the external commissioning phase.
Routing an internal infrastructure alert across the public internet back to the vendor seems to directly violate all the isolation principles we just discussed.
It does sound like a contradiction at first.
What is the technical justification for doing that? Why break the seal?
It is the absolute final validation of the telemetry loop.
Okay.
Think about it. Before you hand a 500-rack AI cluster over to a production environment, you have to definitively prove that the entire alert chain functions mechanically.
Right. You have to know the alarms actually ring.
So you simulate a critical failure, perhaps triggering a fake thermal alert on a CDU.
And drill.
Right. The physical sensor sends the data to the SCC worker node. The alerting algorithm processes that data. The pod hands the payload over to the SMTP relay.
And then the relay has to actually send it.
Right. The relay traverses the customer's outbound firewall. and the email successfully lands in a Supermicro engineer's inbox.
Ah, so it verifies that the customer's corporate firewall isn't silently dropping the outbound SMTP traffic.
Exactly. If you only test internal routing like sending the alert to a local admin, you might completely miss a strict egress rule on the corporate firewall that blocks port 587 to the outside world.
And you wouldn't know until a real emergency happened and that the email couldn't get out to the vendor for support.
Exactly. By forcing an external transmission during setup, they validate end-to-end functionality.
That makes a lot of sense.
And once that commissioning alert is verified and received, the external routing is immediately disabled and the system is permanently locked down to internal recipients only.
So they just open the door, test the alarm, and lock the door again.
Exactly.
Validating that alert chain during commissioning ensures that the platform is actually ready for day 2 operations.
Which is critical.
Which is the clear focus of Draft 8 and Draft 1.
Oh, absolutely.
Reading these forms, they are not just interested in getting the cluster turned on and leaving. They are obsessed with how the cluster will behave 12 to 24 months from now.
Because day 1 is just the deployment.
The easy part, relatively.
Right. Day 2 represents the entire ongoing operational life cycle of the platform.
And the surveys force the customer to think about this up front. They have to define the, quote, target node count, 1224 mode, alongside the initial day 1 deployment numbers.
They want to know the growth plan immediately.
They demand a specifically named day 2 operations owner, a team, or a vendor.
Someone has to be responsible.
They require specific checkbox configurations for air, liquid-cooled, GPU, and CDU infrastructure.
Yeah.
And Draft 1 includes this massive warning regarding capacity planning.
The sizing warning.
Right. It states that sizing must be continually reviewed during deployment and early production to avoid undersizing or oversizing.
It's not a set-it-and-forget-it system.
No. The specific quote is, 2 deployments with the same number of system nodes may not consume the same SCC resources.
That sentence right there is the absolute key to understanding the fluid nature of AI workloads.
It forces the architect to acknowledge that hardware parity does not equal telemetry parity.
Exactly.
But how does that work? How can 2 identical 512-node clusters generate vastly different loads on the management infrastructure?
It depends entirely on the workload scheduling.
The software they run?
Exactly. Consider Cluster A, which is totally dedicated to foundational model training.
Like training a massive large language model from scratch.
Right. A training run is a highly synchronized, incredibly aggressive workload.
Okay.
All 512 nodes will spin up their GPUs to maximum utilization simultaneously.
So the power draw spikes violently all at once?
Yes. The thermal output peaks instantly across the floor, and the CDUs have to dynamically increase the liquid flow to compensate for that sudden wall of heat.
The physical environment goes from 0 to 100 in seconds.
And because of that, every single hardware component begins firing high-priority telemetry data simultaneously to report its new state.
I'm hot, I'm pulling power, I'm pumping water.
Exactly. The SCC cluster experiences a massive immediate surge in data ingestion.
A tsunami of JSON payloads.
Exactly. Now, consider Cluster B. Identical hardware, same 512 nodes. But this one is dedicated to inference workloads or maybe asynchronous batch processing.
Just answering queries like ChatGPT generating a response?
Right. The utilization there is steady, it's localized to specific nodes as requests come in, and it's much more predictable.
Ah, so the thermal dynamics are much more stable.
They are.
The telemetry stream is just a steady, manageable flow rather than a synchronized burst.
Exactly. Therefore, the SCC Kubernetes cluster for the training environment Cluster A might require 12 worker nodes just to handle the burst telemetry and the database write speeds during that massive training spike.
Just to keep up with the noise.
Right. While the inference cluster, Cluster B, might operate perfectly well on just 3 worker nodes.
Even though the physical metal on the floor is exactly the same.
Exactly. You cannot statically provision the management plane based just on hardware. It must be elastic.
The watcher has to adapt to the behavior of the watched.
It's a living system.
The document explicitly mandates reviewing the sizing during early production, because the only way to truly know the telemetry volume is to observe the cluster under a real-world workload.
You have to watch it sweat.
You might discover that your polling frequency is just too aggressive, forcing you to suddenly scale the worker nodes up to prevent a telemetry backlog.
It requires continuous operational tuning.
Constant vigilance.
The documentation is forcing the customer to build a framework for ongoing capacity management, ensuring the monitoring layer scales seamlessly alongside the AI workload.
It really is a masterclass in anticipating the realities of physical infrastructure.
It's brilliant engineering.
Think about the journey we just took through these forms. We started by looking at the staggering compute power required simply to ingest AI telemetry, the dual 32-core processors handling millions of data points.
Just to watch the system.
We explored how the thermal limits of the hardware dictate the physical rack geography, literally forcing massive deployments to spread out over the floor and rely on complex liquid cooling loops.
Because of the 100-kilowatt power densities.
Right. We analyzed the rigid, paranoid requirements of Kubernetes subnet isolation and the severe consequences of overlapping CIDRs.
The whole system crashing because of one bad IP address.
We examined the friction between bleeding-edge telemetry and legacy enterprise protocols like SMTP and LDAP, including, the very human vulnerabilities of deployment logistics and typing passwords into Excel.
The weakest link.
And finally, we looked at the absolute necessity of elastic capacity planning for day 2 operations, adapting to the highly variable nature of AI workloads.
These documents, boring as they look on the surface, they really provide a rare, completely unvarnished look at the physical scaffolding required to support this whole AI transition.
It's incredible, and I want to leave you with a final thought to consider as you interact with the digital systems around you today.
Yeah, this is important.
We have this tendency, right, to talk about AI purely in the abstract.
Oh, all the time.
We discuss neural networks and parameter counts and algorithmic breakthroughs as if they exist as pure math.
Magic.
Like they are weightless and ethereal, just living somewhere up in the cloud.
Right.
But analyzing these deployment blueprints proves without a doubt that the cloud is an illusion.
It really is.
The reality of artificial intelligence is incredibly heavy iron.
Heavy hot iron.
It is miles of specialized liquid cooling loops, 100-kilowatt power distribution units, and an almost paralyzing degree of network complexity.
It's a massive industrial factory.
And the paradox of the AI revolution is this. As our software becomes more abstracted, more autonomous, and more capable in the digital realm, it is simultaneously forcing humans to become more exacting, more physically precise, and hyper-organized in the physical realm.
Just to keep the underlying machinery from melting down.
Exactly. The intelligence may be artificial, but the infrastructure is undeniably physical. Keep questioning the unseen systems around you, and we'll see you next time on The Deep Dive.